Hey everyone, and welcome back to the channel where we dive deep into the science that's not just interesting, but the kind that might actually change everything we thought we knew. Today, we're talking about something that sounds like it's ripped straight out of a sci-fi novel, but it's happening right now in labs across the globe. It's a story about a tiny piece of silicon, a computer chip, that might be doing the utterly impossible. Imagine for a second the biggest, most powerful machines humanity has ever built. The ones that accelerate particles to near light speed, crashing them together to glimpse the fundamental forces of the cosmos. Think of the Large Hadron Collider, a 17-mile ring buried beneath the border of Switzerland and France, a marvel of engineering designed to explore the very building blocks of reality. Now, picture something infinitely smaller, something the size of your thumbnail, a quantum computer chip. And what if I told you that this tiny chip might be demonstrating physics that, until now, we thought only those colossal machines could achieve? Sounds wild, right? Well, buckle up, because that's the story of the Majorana 1 chip and a potential breakthrough that has the quantum physics world buzzing with a mix of electrifying excitement and intense, necessary skepticism. It might just be a fluke, an anomaly, or it might be the first hint that we need to fundamentally rethink quantum mechanics itself. In science, especially in fields as complex and cutting-edge as quantum physics, progress is often incremental. It's step by step, building on decades of theory and experiment. Genuine breakthroughs, those moments that truly shift the paradigm, are incredibly rare. They're the scientific equivalent of finding a new continent or discovering a new law of nature that nobody saw coming, and the kind of breakthrough that could reshape not just one field, but potentially bridge seemingly disparate areas of physics, like the microscopic world of quantum computing and the high-energy realm of particle physics. That's almost unheard of, but today, that's precisely what researchers are grappling with. They're looking at data coming from this experimental quantum processor, the Majorana 1, and seeing patterns that look eerily like something called Compton Scattering. And if those patterns are telling the truth, this little chip is performing a feat previously considered far, far beyond the capabilities of quantum computers as we understand them. Think about the implications. A quantum device that isn't just crunching numbers or simulating simple quantum systems, but one that seems to be interacting with quantum states in a way that mirrors the high-energy collisions of particles. If this holds up, it could challenge the very foundations of modern quantum mechanics and potentially unlock a whole new era for quantum artificial intelligence. So, what exactly is Compton scattering? And why is it such a big deal if a quantum chip is involved? Compton scattering, a cornerstone of quantum physics at its heart. Compton scattering is a fundamental interaction in quantum physics. It describes what happens when a photon, a particle of light, collides with a charged particle, usually an electron. Imagine light not as a smooth wave, but as a stream of tiny energy packets, like miniature bullets. When one of these photon bullets hits an electron, which you can think of as another tiny particle, a few things happen. The photon doesn't just bounce off like two billiard balls. Instead, it transfers some of its energy and momentum to the electron. This causes the electron to recoil, like being hit by that tiny bullet. And because the photon lost some energy, its wavelength changes. It gets longer. Its direction also changes, scattering off at an angle. This effect, first observed and explained by Arthur Compton in the 1920s, was a crucial piece of evidence that light behaves like both a wave and a particle, a core concept of quantum mechanics. It's a phenomenon we traditionally see in high-energy experiments because you need energetic photons, like X-rays or gamma rays, colliding with electrons to produce a measurable shift in the photon's wavelength and direction. It's physics that happens in particle accelerators, in interactions between cosmic rays and matter, and even plays a role in medical imaging technology like X-rays. It's always been considered firmly in the domain of high-energy physics and quantum field theory. Now, back to our chip. For the first time ever, researchers believe this kind of interaction, or something remarkably consistent with its data, signature, may be taking place within a quantum processor. The term Compton Scattering protocol in this context doesn't necessarily mean the chip is firing photons at electrons like a mini collider. Instead, it refers to a mechanism or process within the chip that simulates or harnesses similar fundamental interactions internally. If this is accurate, it would suggest an unprecedented ability to manipulate quantum information, not just through standard quantum logic gates, like flipping a qubit's state or entangling two qubits, but through interactions that mimic the behavior of real particle collisions at a much deeper level. Imagine the difference between moving chess pieces on a board according to set rules and somehow manipulating the fundamental forces that govern the board and pieces themselves. That's the kind of leap this could represent. The Majorana 1 chip, pushing the boundaries. So, what makes the Majorana 1 chip so special? Why this chip and not any other quantum processor out there? The Majorana 1 represents the absolute bleeding edge of quantum hardware innovation. Unlike standard quantum processors that typically work with simpler, isolated qubits, which are like the basic bits of quantum information, analogous to the zeros and ones in classical computing, this chip was designed from the ground up to work with exotic quantum states. These are states of matter and energy that lie outside the boundaries of classical physics, and even beyond the scope of typical qubit-based quantum computing models. The whispers are that this chip might be designed to utilize things like Majorana fermions. Now stick with me here because Majorana fermions are fascinating and mind-bending. Proposed by physicist Ettore Majorana, these are hypothetical particles that are their own antiparticles. Most particles have distinct antiparticles, like the electron and the positron. A particle being its own antiparticle is a concept that lives deep in the realm of advanced theoretical physics, often connected to ideas about quantum fields and the fundamental nature of reality. If the Majorana 1 is somehow leveraging or even creating a stable environment for these exotic states, it's already operating in a fundamentally different way than most quantum computers. And it was during testing, while researchers were putting this unique chip through its paces, that they started noticing something strange. Patterns in the chip's output, data that they couldn't easily explain with standard quantum mechanics or typical chip behavior. As they analyzed these patterns, they began to see a striking resemblance to the data signatures associated with Compton scattering events. It was like finding a fingerprint at a crime scene that belonged to someone who wasn't supposed to be there. This behavior wasn't expected. It wasn't something they were specifically trying to simulate in the traditional sense. It suggested the chip might be engaging in a new, unpredicted kind of quantum interaction. Such a finding could signify a tangible bridge between the controlled, engineered world of quantum computing and the more complex, probabilistic, high-energy world of quantum field theory. A gap that, until now, has remained largely theoretical. Unsurprisingly, when news of these findings started circulating, the response from the scientific community was immediate and complex. It was a wave of cautious intrigue. On one hand, the possibility of a discovery this fundamental, this paradigm-shifting, is incredibly exciting. This is the kind of stuff that physicists dream about. It could open up entirely new avenues of research, lead to unforeseen technologies, and deepen our understanding of the universe. But on the other hand, there's the deep-seated, healthy skepticism that is the bedrock of the scientific method. Extraordinary claims demand extraordinary evidence. Before anyone gets ahead of themselves declaring a revolution, experts stressed the absolute need for thorough investigation, rigorous analysis, and, most importantly, independent replication of the results. Dr. Elena Vasquez, a highly respected quantum physicist, shared her perspective, capturing this dual feeling perfectly. She noted, "If the Majorana 1 chip is indeed exhibiting properties similar to Compton scattering, it suggests a deeper, more fundamental connection between quantum information and the fundamental forces of nature than we previously understood. This could be a monumental step forward, a truly historic moment. But, and this is crucial, we have to ensure it's not merely an artifact of the experiment. Could there be some subtle error in the setup? Some overlooked environmental factor influencing the data? We must rule out all possibilities. Think about this in everyday life. If someone tells you something truly unbelievable has happened, say, your car suddenly learned to fly, your first reaction isn't likely pure belief. You'd be stunned, excited perhaps, but also immediately start asking questions. How did it happen? Is there a video? Can you show me? Is there a logical explanation I'm missing? That process of questioning, of seeking verification, is what scientists are doing now. Meanwhile, quantum computing experts are just as captivated. Dr. Martin Klein, a specialist in quantum information theory, sees this as potentially the missing piece they've been searching for. He observed, "For years, we've worked with quantum systems that are highly controlled, delicate, almost pristine. High-energy physics, on the other hand, deals with the raw, often unpredictable power of particle interactions and quantum fields. This experiment could be the missing link between these two worlds. It opens up a new frontier, one where we may be able to tap into these more fundamental, possibly more resilient interactions for quantum computation, and the implications for advanced quantum AI, which could potentially learn and interact with complex systems in ways we can't currently imagine, are truly mind-boggling. Imagine being able to build AI systems whose processing power isn't just based on logic gates, but on mimicking the fundamental interactions of the universe itself. It's like moving from building structures with Lego blocks to being able to manipulate the atomic bonds holding materials together." Despite the incredible buzz, that healthy dose of skepticism is not only present, it's actively being applied. Some researchers argue that the observed effects, while intriguing, could stem from a mundane experimental anomaly. Maybe there's a subtle flaw in the measurement device, or an unexpected environmental interaction, like stray electromagnetic fields, that's mimicking the Compton signature. Or perhaps the data, complex and noisy as quantum data often is, has been misinterpreted. Dr. Anil Kapoor, a leading researcher in quantum electronics, voiced this crucial, cautious perspective. Breakthroughs like this are sometimes, regrettably, the result of subtle quirks in the experimental setup that are only discovered later, she stated. It's why the scientific community has that old adage, extraordinary claims demand extraordinary evidence. One lab's finding, no matter how exciting, needs independent verification across multiple labs, using different equipment and methods, before these results can be fully accepted as fact. This ongoing debate, this back and forth between groundbreaking, possibility, and rigorous demand for proof, is vital. It is the scientific process in action. It highlights just how potentially revolutionary the Majorana 1 chip's behavior could be. If the chip truly exhibits quantum interactions analogous to Compton scattering, it wouldn't just be a triumph in engineering, building such a complex device. It could fundamentally reshape our theoretical understanding of quantum systems, revealing connections we never suspected. How could a quantum chip unlock a high-energy physics protocol? This is perhaps the greatest mystery at the heart of this discovery. How could a device as small and precisely engineered as a quantum chip possibly replicate a phenomenon typically reserved for massive, multi-billion-dollar particle accelerators? It's like expecting a finely tuned wristwatch to somehow generate the power of a lightning bolt. One leading theory, as mentioned before, centers around the unique design of the Majorana chip and the exotic quantum environment it creates. Unlike standard qubit systems that try to isolate quantum information as much as possible, this chip might be engineered to facilitate more complex interactions with the surrounding quantum vacuum or quantum fields. By utilizing those exotic quantum states, potentially involving Majorana fermions, the chip might be reproducing the incredibly complex energy density or interaction conditions required to mimic or even trigger Compton scattering-like events internally. It's not just about the particles in the chip, but the environment the chip creates around them. It's as if the chip acts as a miniature controlled pocket of space where these fundamental interactions are more likely to occur or become visible. Think of it this way. You can't create a thunderstorm in your living room, but if you could create a miniature environment with precisely the right atmospheric pressure, humidity, and charge separation in a controlled box, you might be able to generate miniature lightning. The Majorana chip might be doing something analogous at the quantum level, creating the specific conditions for Compton-like interactions to occur on a chip scale. This remains speculative, of course. The exact mechanism is still part of the mystery being investigated. But the idea itself is breathtaking. If these findings are validated through replication and further study, the implications could be nothing short of staggering. They extend far beyond just making faster computers. New energy technologies. Compton scattering is fundamentally about energy exchange. A photon gives energy to an electron, and vice versa, in certain related effects. By understanding and potentially controlling how this kind of energy is exchanged during quantum-level, Compton-like interactions within a chip, we could open the door to radically new methods for energy transfer, storage, and conversion within quantum systems. Could this lead to hyper-efficient quantum batteries? Novel ways to extract or transfer energy at the nanoscale? The potential is immense and could lead to technologies that are orders of magnitude more efficient, sustainable, or even revolutionary compared to what we have today. Imagine harnessing energy directly from fundamental quantum interactions. Beyond speed limit computing? This is where things get really speculative, bordering on science fiction, but the article does raise the question. While still highly theoretical and not supported by current evidence, some researchers wonder if manipulating quantum states in this way, tapping into interactions that are fundamentally related to energy and momentum transfer, could somehow challenge current limits on computing speed. Could this one day lead to processing information at speeds previously thought impossible, perhaps even hinting at connections to relativistic effects? It's a wild idea, one that requires significant leaps in understanding. But the possibility is no longer entirely outside the realm of discussion when you're talking about Compton-like interactions. Bridging quantum and particle physics. This is perhaps the most immediate and significant theoretical implication. A successful demonstration of this Compton scattering protocol on a chip could serve as the first real, tangible bridge between the highly controlled, engineered world of quantum computing and the study of fundamental particles and forces described by quantum field theory. This would represent a monumental unifying breakthrough. It would allow for incredible cross-pollination between fields that have long operated largely in parallel. Imagine physicists who study particle collisions using quantum computers not just for simulation, but potentially as experimental platforms to test theories in new ways. And imagine quantum computer scientists gaining insights from particle physics to design entirely new types of quantum processors. Evolution of quantum AI. As Dr. Klein mentioned, this could profoundly impact quantum AI. Current quantum algorithms are often abstract mathematical constructs. But if AI could be built on a foundation that directly mimics or harnesses fundamental physics interactions, the very processes by which nature itself computes and interacts, it could lead to algorithms and learning models that are fundamentally more efficient, adaptive, and powerful. Quantum AI that learns by interacting with a simulated or actual quantum environment at the level of particle-like collisions. That's a concept that could redefine machine learning. But, and it's a big but, let's pump the brakes slightly on the wildest speculations. As exciting as the possibilities are, it's crucial to remember that this is still early days. The skepticism isn't just healthy, it's necessary. Some theorists suggest that what the researchers are seeing might not be Compton scattering at all. Instead, it could be a more mundane, albeit still interesting, quantum effect that has been misinterpreted. Quantum systems are notoriously complex and prone to noise. Subtle vibrations, temperature fluctuations, stray electromagnetic fields. All of these can influence delicate quantum states and produce strange, misleading data signals. What looks like a Compton signature could be a sophisticated form of noise or a signal distorted by these experimental conditions until more data is gathered, meticulously analyzed, and most importantly, validated across multiple independent labs. These ideas remain speculative. They are undeniably worth exploring because the potential is so high, but they must withstand the absolute scrutiny of the scientific method. If multiple research groups, using their own equipment and running independent experiments, can replicate the findings, seeing the same Compton-like signatures from a similar chip design, then the evidence will become extraordinary enough to support the extraordinary claim. That's the stage the scientific community is eagerly, cautiously waiting for. And if this does turn out to be real, even if it's a slightly different phenomenon that simply resembles Compton scattering but is still a novel, high-energy-like interaction on a chip, then the implications are even more profound than we can currently imagine. It could force us to rewrite textbooks, redefine the capabilities of quantum hardware, unlock unprecedented power for quantum AI, and perhaps even shed light on the fundamental architecture of physics itself. This story of the Majorana 1 chip, the potential Compton scattering protocol, and the scientific world's reaction offers us some powerful lessons, not just about physics, but about life itself. Embrace the unknown. This discovery, if real, comes from pushing into territory that was previously considered impossible. It reminds us that our current understanding of the universe is incomplete. There are vast frontiers of knowledge waiting to be explored, things that will challenge our most deeply held assumptions. We shouldn't be afraid of the unknown. We should be curious about it. In our own lives, this means being open to new ideas, experiences, and perspectives that might challenge what we think we know about the world or ourselves. Value healthy. Skepticism, the scientific community's reaction, isn't just excitement, it's also rigorous doubt. They aren't just accepting the claim. They are demanding proof, replication, and alternative explanations. This is a crucial lesson for all of us. In a world flooded with information and sensational claims, it's vital to maintain healthy skepticism. Don't believe everything you hear immediately. Ask questions. Look for verification from multiple reliable sources. Understand why a claim is being made and what evidence supports it. This critical thinking isn't cynical. It's essential for navigating complexity. Curiosity is a superpower. This potential breakthrough started because researchers noticed something strange in their IB data and got curious. They didn't dismiss the strange patterns. They investigated them. Curiosity is the engine of discovery, whether it's unlocking the secrets of the cosmos or understanding why something works the way it does in your everyday life. Stay curious about the world around you. Ask why and how. That simple act of questioning can lead to incredible insights and growth. Progress takes time and collaboration. No single scientist or lab makes a breakthrough like this in isolation. It requires years of foundational research, sophisticated engineering, careful experimentation, rigorous analysis, and the collective effort of a global community to debate, scrutinize, and ultimately, hopefully, validate the findings. Big, important. Advancements are rarely solo acts. They are built through collaboration, peer review, and sometimes intense debate. This reminds us that tackling complex problems, whether in science or in society, often requires working together, sharing ideas, and challenging each other constructively. The universe is more astonishing than we can imagine, even if this particular finding turns out to be something less dramatic than Compton scattering. The fact that researchers are exploring possibilities like chips interacting with exotic states or mimicking high-energy physics on a miniature scale is a testament to the incredible mind-bending nature of the quantum world. There is so much wonder in the universe waiting to be discovered. Stay open to that sense of awe and possibility. So, the question remains, hanging in the air like a superposition state waiting to collapse. Is the Majorana 1 chip the first true, tangible bridge between the microscopic laws that govern computation and the colossal forces of the quantum cosmos? Is it the first step towards a future where quantum computers don't just process information, but interact with the fundamental fabric of reality in ways we've only dreamed of? Time, more experiments, and the rigorous process of scientific verification will ultimately tell. But the journey of exploring this possibility? It's already changing how we think about what's possible. If this discovery and the potential it holds for rewriting physics, quantum AI, and the future of technology has you as captivated as it has the scientific world, then you are exactly where you need to be. This is the bleeding edge. This is where the future unfolds. Right now, we'll be here, breaking down the science, exploring the implications, and keeping you informed on the most thrilling breakthroughs in physics, AI, and the quantum revolution. So, if you haven't already, please hit that subscribe button and join our community of curious minds. Don't miss out on the next astonishing chapter in this incredible scientific story.